welcome to lesson 23 of the course on industrial automation and control. Today we will be talking about CNC machines, that is computer numerically controlled machines. So, as usual, let us look at the instructional objectives of this lesson. So, after learning the lesson, the student should be able to describe the main features of a CNC machine, what makes it, describe its main advantages, why we should spend money to buy these machines, they are very expensive, explain the main features of part programming, because these machines are automated, they can be programmed. So, the programs are called part programs. So, we will see some basic features of part programming, and finally the drives. The CNC machines create motions, all machines create motions, machines especially which are used for manufacturing. So, naturally they involve drives, the technology which generates the power and the control for creating precise motion against heavy loads. So, we will see these drives, and we will see the requirements on the CNC drives, so that later on when we study the drive technology, we can refer to that and we will see how these drives are actually realized using electrical machines, power electronics and controls. So, let us first look at a machining process, right. So, basically in a machining process we are talking about manufacturing, typically metallic materials. So, essentially it is taking a piece of metal and removing metal from that precisely, so that you get a part of a specific geometric dimensions. So, essentially it is metal removal, which means that actually it is removal by a tool which is made of very hard metal, things like carbide, diamond, etc. So, so essentially you have to produce relative motion against of the job and the tool. So, there are various kinds of machining processes. The most common is turning, which we see in lathes, in lathe machine. So, in lathe machine what happens is that you have this is the workpiece which is held in a holding mechanism, typically known as the chuck. It is known as the chuck, and the chuck is rotated by a spindle, which is here there is a drive motor. So, we have a motor drive here, and so the workpiece is rotating, and this is the tool, this is the tool holder which moves. So, the tool holder can move this way, can move. So, therefore, for example it can be used to reduce the diameter of the workpiece. So, as this thing rotates and the tool moves from this end to that end with a certain degree of penetration. So, this much of metal will be removed from both sides. So, after the tool moves one cycle, the diameter will get reduced to this, right. So, this is the way turning produces. Now, then typically, so in this case note that it is the workpiece which is rotating, driven by the spindle, while it is the tool which is having rectilinear motion. On the other hand, if we take another machining process called milling, there you have a cutter. So, this is the milling cutter which has sharp teeth and which is driven by the spindle, and it is the job, this is the table, this is the job workpiece which is having rectilinear motion, and generally two dimensional rectilinear motion. It can move this way, that way, and the table can move this way, that way also. So, you can create 2-dimensional motion and the cutter is rotating and steady in one location. So, you see the compared to turning, it is the in turning it was the workpiece which was rotating, here it is the tool which is rotating. So, it can happen both ways. For example, if you take another process called drilling. So, in a drilling also it is the workpiece which has 2-dimensional motion, and because you may like to drill a hole anywhere on the workpiece. On the other hand, the workpiece is rotating at generally at very high speed, it is rotating, at the same time it can come down to actually drill a hole. So, the workpiece in this case is capable of, it has a high speed rotation and it can also move along one axis, whether the the tool can move along one axis and while rotating, and the job can move in have rectilinear motion, have motion a 2-dimensional motion, right. So, which means so this shows that that any metal cutting machine would require motion for the tool and would require motion for the workpiece, and these motions naturally have to be very precise. Number 2 is that for quick cutting there has to be a, so these are generally parameterized by quantities like speed, which is related to the cutting speed of the rotating body. Then it could be, then there is something called feed. So, feed means that the stroke of it can be the linear motion of the tool in the case of, so per rotation, by how much does the tool move in the case of turning, or by how much does the job move in the case of milling, or depth of cut. So, how much in one complete cycle of motion, how much material, how much depth of material is removed. So, such parameters are set typically in such machines, and naturally you can understand that even if we want very good surface finish, we generally we cannot give very high depth of cut, but so for rough cuts we can, for quick production we can give high depth of cuts and high feeds. So, naturally that will, you are removing metal like steel, so naturally it puts a lot of load on the drive. So, the idea is to create very precise motions against very high loads. So, the workpiece, this typically shows this shows how the movement is created. So, the rotation is actually very simple, it is just connected to the shaft of the spindle drive motor. So, as the motor rotates, the tool in the case of milling or the workpiece or the chuck in the case of turning will rotate. That is very simple. For creating the 2-dimensional motion of the table, this kind of a mechanism is created where there is a slide. So, this slide can, we are only showing motion in one direction. So, in this direction slide can move along this, because it is connected to what is known as a ball screw. So, this is a ball screw. So, the drive is still a motor. So, there is a motor which is coupled to the ball screw, maybe through a gear. So, as the ball screw rotates, this slide can move this way or that way, just like a screw motion, and these ball screws are very well designed such that there is the precise motion is created, and things like backlash which affect the accuracy of manufacturing are minimized, and they can be minimized, they are actually minimized by engineering design, and whatever remains can be also mostly compensated in these machines. So, to summarize, if you look at the feature of the machine, then we have to create rotational motion which is created by the spindle drive, we have to create linear motion which is created by the table drive, and in the table drive basically the drive is rotational, there is a linear motion conversion using ball screw or rack pinion, generally ball screw gives better accuracy, and guideways, so that the there is no transverse motion, motions are strictly in the direction in which the drive is provided. These drives that are employed are generally servo motor drives, because you need to have precise motion control and you need to have good transient response, because drives have to be very precise position control is required. So, therefore, they have to start and stop at the right moments, and sometimes even speed ratios have to be maintained along the two axes for cutting things like surfaces, say cylindrical surfaces, or cutting corners. So, we employ servo motor drives, DC drives, stepper motor or AC drives. For very large machines you can have hydraulic drives also, but generally we employ DC and AC drives. For very small things stepper drives are used, but they are generally not of that high rating. So, therefore, DC and AC drives are generally used, mostly DC drives, DC and BLDC drives, brushless DC. So, we will see these drives in detail, in some more detail in our lessons on drives. Then you naturally you need feedbacks. So, you have digital feedbacks like shaft encoders, or you can have resolvers. Sometimes you can have position sensor like LVDTs or potentiometers, etc. So, you need basically you have to create rotational linear precise motion. So, you need precise drives which are created by motors, and you need speed and position feedback. So, they are provided by the sensors, and similarly you have mechanical arrangements which create precise motion like ball screw, etc. So, these are the major parts in the machine. Of course, there are various kinds of auxiliary parts, like for example, there is very high heat generation at the tool workpiece interface. So, there is coolant has to be applied, liquid coolant has to be applied directly at the tool job interface, so that the interface does not heat up, because that will affect the quality of machining. So, there is a coolant, plus there are all kinds of other things like for automation there is whole automation setup where somebody can enter programs. So, there is an operator display, there are all kinds of protection mechanisms. So, they are the auxiliary components. Plus there is power. So, actually these machines, it was soon developed, it was soon understood that there is a lot of things to be gained if we can control the machines precisely using digital techniques, and finally by computer like components like especially microprocessors can be interfaced to it. So, this kind of controllers would lead to very precise control of the machine, which is not possible, generally not possible by a manual operator. So, it was soon realized that these systems can lead to very high quality engineering and also reduce unproductive time. Now, this term numerical control has been defined by the EIA as a system in which actions are controlled by direct insertion of numerical data at some point. So, at some point numerical data must be used to control the machine, and the system must automatically interpret at least some portion of this data. So, even if you do not have a computer, you can have a paper punch card reader. They are the ordinary. They were the early versions of the CNC machines. So, even if you have a paper tape which is punched, and there is to be a paper tape reader, and that reader is to create the motion. So, even if there is no explicit electronic computer, here also in the paper tape you are there is some numeric data which is punched, and according to that numeric data the machine was controlled. That is why it is called numeric control. But in modern machines these things do not exist at all. Modern machines are all computer controlled. So basically computer numerically controlled means that computer controlled. So it can be it is generally a microprocessor, it may be an industrial PC, sometimes there will be a PLC. So various kinds of industrial computers are used. So it basically is meant to replace manual actions of operators, and so the instructions to the machine which are required for its operation are written in the form of a kind of program called part programs, which describe the activities which are interpreted and executed by the machine. So we'll see little later what kind of things can be done using part programs. Typically, these CNC machines are very expensive. So it's not that everybody can afford it, or that for every kind of manufacturing operation one has to procure a CNC. So CNC will be good for parts processed frequently in small lots, because if you process parts frequently in small lots, then you will, if you don't use automation, then you are going to end up spending a lot of time by lot of setup time. So every time you have a new lot, you will spend a good amount of time in setting up. Then you will manufacture, since the lots are small, so you are going to manufacture a little while, and then again you have to spend time in setup. So the actual productive time of a machine, which is just the time when it cuts the metal, is actually reduced. So therefore the CNC machine is suitable for this, because it cuts down that setup time significantly using automation. But the part geometry is complex, so you don't have to really rely on the operator skill. You have to just produce a correct part program, and if the part program is correct, then the machine being automated will absolutely correctly will produce that geometry irrespective of the operator skill. Tolerances are closed because the kind of controls that you apply are so sophisticated that it is not possible for manual operators to apply such controls, and therefore very high compliance to the tolerances can be realized. When there are several operations needed on the part, again it is related to setup time. You may need to have various kinds of tools working on that. So therefore again you will lose a lot of time by changing tools, while with the things like technologies like automatic tool changers and wide variety of tool magazines, this tool changing is generally achieved very efficiently in CNC machines. And parts are expensive, because when parts are expensive, you don't like to take a chance that due to faulty manufacturing some part will get wasted. So that's why you take help of a machine which once it is set up properly, it will go on working and producing the parts without any mistake or failure. When engineering design changes are again likely, again this is also related to setup time. So you see that there are basically 2 points. One is situations where a good amount of setup time is required, and secondly where situations where very high skills to cater to complex geometry and close tolerances are required. So it is for these 2 reasons that CNC score over non-CNC machines or manually operated machines. So from advantages and disadvantages, you have flexibility is one advantage which is achieved by programming, and so you can easily change just change a program and your whole setup will get changed. Or you can have pre-stored programs which can be just need to be loaded, which is a much faster operation. Disadvantage is and of course accuracy, flexibility and accuracy. Disadvantage corresponding disadvantages could be one is cost. So these machines are very expensive and they have very high costs, and maintenance. So you need very expert maintenance for these machines, because if they are not maintained properly, then they are going to be damaged, and then finally they will lose their accuracy and things like that. So overall productivity is much improved due to reduced setup time, automated tool changing, which is again reduces setup time, I mean unproductive time. Sometimes some of these machines will have inherent material handling. So, if you want to change a tool, the machine will stop the machine, take out the tool, put it in the tool magazine, bring out another tool. So, all these material handling work will be done by the machine itself. Scrap rate is reduced because you must have, it is assumed that the part programs are written with carefully using scientific optimization methods. So, from a given piece of material, because you are not going to you have much more precise operation. So, you can have optimal material utilization, therefore, scrap rate will be reduced. Manpower is reduced because much of the work in these machines can are done automatically. Sometimes you program a machine for a day and feed it with enough work material once at a time, and then run it whole day without any kind of supervision or any kind of operating personnel. These machines can go on manufacturing one after the other the parts. They have reduced downtime because these are the benefits that you get by paying that high sum of money for its cost. So, downtime is reduced because these machines are very well made, their engineering is very strong. On the other hand, the disadvantage is that the operation of these machines and maintenance require very highly skilled operator, not only just skilled in operation, but in various other kinds of technologies. For example, part program writing, etc., they may require skilled operators. So, these are so we have seen that CNC machines in many situations are amply justified. So, now we will see that what kind of motions these CNCs can be created such that automatically parts can be manufactured. So, there are generally two kinds of machines. One kind of machines are capable of making point to point motions. So, typically used in drilling. So, you say that drill a hole here, then a hole here, then a hole here, here and here. So, this is, so you are just specifying certain points. So, the machine is coming to a point, doing a certain operation, then again going to another point and doing another operation. So, the operations that the machines are doing are essentially point operations like drilling. On the other hand, you can have systems where you can specify the start point in the coordinate space, the end point, and then specify some kind of interpolation, let us say a circular interpolation. So, the machine will start from here, and depending on your instruction will cut an arc. Suppose we are talking about circular interpolation, will cut an arc from here to here, or it could also cut an arc. It could also cut an arc between these 2 points. So, that depends on what you have specified. If you have specified a clockwise arc, then this will be drawn. If you have specified an anti-clockwise arc, then this will be cut. So, these are called contouring systems. You can note that here the controlled cutting goes on throughout the journey, and to be able to achieve certain kinds of profiles like a circle, the x and y axis drives for the table have to be very coordinated to be able to get that contour. So, it is fundamental to define coordinate systems because all the part program instructions are given, most of them are involved, especially the main cutting instructions, part program instruction, all involve various coordinates. So, the coordinate space is actually very simple. So, this is like x, I am sorry. So, it is like x in this direction, y in this direction, and it is a right handed coordinate system. So, therefore, z will be the vertical direction, and therefore, you can also have you can also similarly define rotational directions. So, if you take again a right handed system, then if you curl your fingers around this, then the positive direction, this direction is positive, where the thumb will point towards the positive z axis. So, these are given according to that. So, these will be positive rotations and these will be positive translations. Then all these points and coordinates which are mentioned are can be mentioned in two ways. One is an incremental or an absolute system. Generally the absolute system is preferred. So, you see that if you want to specify the x axis coordinates of these 4 points, then in the incremental system you will say, suppose this is x, here the x coordinate is x. So, this is going to be say x plus 300. Similarly, this is going to be, and once you have done x plus 300, now your current position is at 1. So, now x is the x coordinate of this point is x plus 300 and the coordinate of this point is x plus 500. So, in the incremental system you always do it from the current point. So, the current point is here. So, this is going to be 200. So, therefore, the next instruction to the machine will be x plus 300, actually this should have been 200. So, x plus 300, x plus 200, then you have come to this point, and then if you want to go to 3, then you have to do x minus 300, and then from 3 to 1 you have to do x minus 200. So, you got to go this way. On the other hand, if you are using absolute, then you just always do it from a stationary origin that you have assumed in the coordinate space of the machine. So, this is going to be, so the 4 coordinates are going to be x plus 300, x plus 500, 300 plus 200 is 500, and then this is again x plus 200 because this is 200, and then finally x. Now, why the absolute system is preferred? Because suppose you are trying to hole a drill at these locations. So, even if this location is in error, this location will not be if it is an absolute system, but if it is an incremental system, then if at one point the geometric coordinates are not the same, then there is a high chance that all other geometric coordinates will also get affected if the system of providing coordinates is incremental. And this exposition, there will also be a unit. So, these expositions that are meant will be typically mentioned, are generally mentioned in terms of what is known as a basic length unit. So, a basic length unit is the, suppose you have a shaft encoder. So, the shaft encoder gives say 500 pulses per revolution. Let us do this to understand what is the basic length unit. So, suppose shaft encoder gives 500 pulses per rotation. On the other hand, the ball screw or the ball screw pitch is say 1 mm. So, 1 rotation is equal to 1 mm advancement, 1 mm displacement. So, now 1 pulse of shaft encoder is equal to 1 by 500 mm is equal to 0.002 mm, right. So, this is the basic length unit. This is the smallest unit of displacement that this is the smallest displacement that the machine can be aware of, because this will be 1 pulse of encoder. So, that is the smallest, and that is called the basic length unit. So, all these are generally stated in terms of the basic length unit. Similarly, if you have circular interpolation, then you have to give the start time, I am sorry, So, you have to give the start coordinate, you have to give the end coordinate, and you have to give the this is going to be a circular arc. So, you have to give the coordinate of the center or rather the distance, not coordinate, distance of center from x and y. And you can sometimes you are also given, if this is given, you should be able to draw the circle. Sometimes the final point is given. So, this is the final point. So, given these, you can try to, and taking this as center, we have to draw a circular arc and take the tool along this circular arc. So, this is the way typically the circle parameters are specified. So, this I and j will give the coordinate of the circle, this k and ke will give the two endpoints, and then you can either draw the circle like this also. So, whether you will, this is start. So, if you want to draw this circle, then you will go this way, which is clockwise. If you wanted to draw this circle, then you will go anti-clockwise. So, it needs to be mentioned whether the circle has to be drawn in clockwise or in anti-clockwise direction. Accordingly, either this one or this one will be manufactured. So, these are the various circular interpolation directions. So, along the various axes.